This is a video for advanced pre-calc on section 4.1, and first thing you want to do is pause this video and go through number 1, which is an example of a composition of functions. And once you do that, you can resume here. Okay, so if you went through number 1, hopefully you saw that these two functions are inverses of each other. They undo each other. And so let's recap a little bit about, inverses. What is an inverse? An inverse, we could say it undoes a function. The domain and range completely flip when you are for an inverse of a function. The domain and range are switched. When does not all functions have inverses. When a function has an inverse, we call it invertible. Well, in order to have an inverse, a function must be one-to-one. And what that means is every x value goes to a unique y value. So something that would fail to have an inverse would be a parabola. So the most basic being, say I had this function f of x equals x squared. The reason this is an invertible by this definition here is the fact that -2 goes to 4 as well as 2 also goes to 4. And that's a problem because an inverse switches the x and y's or switches the domain and range. And look what happens if I do that with these 2 points. I get 4, -2 and 4, 2. Well, that function, the inverse now, would no longer be a function because you have an x value going to more than one y value, which is a real problem. So you need everything to be unique. Every x value, again, goes to a unique y value. Graphically, something has an inverse if it passes the horizontal line test, meaning, let's look at y equals x squared to show you. In order to be invertible, any horizontal line that I would draw has to cross the graph at most once. And notice this is failing here. Whereas something that is invertible would be like the function y equals x cubed. And if I look at that graph here, any horizontal line I draw at most crosses the graph once. It's just saying that nothing repeats. So y values aren't repeating. Of course, to be a function, x values can't repeat. Okay, so let's go to part C. If you were to graph a function and its inverse on the same axes, what would the symmetry be? Well, because you're flipping x and y, the symmetry should be across the line y equals x. So it should be symmetric across the line y equals x, meaning if I folded the graph across that line y equals x, the function its inverse should line up. How do you find an inverse of function? Well, hopefully you remember from last year, the easiest way to find an inverse was to switch x and y, because remember, domain and ranges get switched. Switch x and y and solve for the new y. How do you prove two functions are inverses? Well, you formally prove it, say you were by doing the composition both ways and showing that they undo each other, meaning that you would get x. So say we're talking about two functions f and g. To prove their inverses, I would have to show that f of g of x equals x and g of f of x equals x. Like problem 1. We got that in problem 1. By doing part B and C in problem 1, we were able, and getting x both times, that proved that those two functions are inverses of each other. So the composition both ways has to produce x. All right, let's do a warm-up, and then you can go through the practice problems. Okay, so the warm-up, flashback to the last unit. Graph this rational function. So kind of quickly going through our steps here. There's nothing to factor. So the y-intercept here, when I put in 0 for x, I get 0, -1/2. There's just one x-intercept where the numerator is 0, so -1/3, 0. There's a vertical asymptote where the denominator equals 0 at x equals 2. the degree in the numerator and the denominator both 1. So the EBA will be, in this case, y equals 3. Let's quickly see if it crosses that EBA. So 3x plus 1 over x minus 2, does this ever equal 3? And when I multiply across, I get 3x plus 1. Will that equal 3x minus 2? X's cancel. I have a false statement, so there's no crossing that EBA. All right, I've got all I need to graph this. So let's see, let's just do my x-intercept is -1/3, y-intercept is -1/2. We've got a vertical asymptote at 2. And the EBA is that horizontal line, y equals 3. And I can already tell what's going to have to happen for this graph. I have no x-intercepts to the right of the vertical asymptote, so I've got to be up here. And then it should change sign across the vertical asymptote. So I'm down here, going through the y and x-intercept, and going back towards the EBA. All right, so that's my graph. Does f have an inverse? It does. Looking at this graph, it passes the horizontal line test. Any horizontal line would at most cross this graph once. So yes, passes the horizontal line test. The function is 1-to-1. All right, let's now find the inverse. So we're going to switch x and y. So x equals 3y plus 1 over y minus 2. Now we've got to isolate y. So if I multiply both sides by y minus 2, I get xy minus 2x equals 3y plus 1. So notice y is in more than one term. So in order to isolate y, you want to get everything with y on one side and everything that does not contain a y on the other side. And then here, notice on the left, I could factor out a y. And now I divide both sides by x minus 3, and I've got my inverse is equal to 2x plus 1 over x minus 3. And that's it. So say you had brought the y's to the other side, you would have gotten, which is equivalent, -2x minus 1 over 3 minus x. How do I get from one to the other? Well, if I just multiplied the top function by -1 over -1, you get the second. So don't get worried if you have something that looks similar but different in signs. It could be you just brought things to the other side. Just try multiplying your function by -1 over -1 and see if you got what I got. Or if you're comparing it to a partner, you can check that too. Okay, so just eyeballing this, by the way, I noticed that looking at part A, the domain of this function, I can look at the graph too, actually. The domain is everything but 2. That should be the range of my inverse. And it looks like that's going to be the case because there's going to be a horizontal asymptote at 2. And it's probably not going to cross it, given that it's the domain of the original. It shouldn't cross it. The range of my part A, my function was everything but 3, and that should be the domain of my inverse, which it is. So sometimes when people are having trouble finding the range of a function, because remember that's the most difficult to find usually, then they may see if the function's invertible, they may decide, okay, let me find the inverse because the range of my original function will be the domain of my inverse. So sometimes that's a helpful tool. All right, last question. How would you check your work and prove that you indeed found the correct inverse? So to check here, I would make sure that f composed with f inverse of x produces x, and the same with f inverse composed with f of x should produce x. And that's how I would check. Okay, so now try the practice problems. It shouldn't take you too long, but try those out, and I'll post solutions.